Today we are seeing about the multi-level inverter, that is 9-level multi-level inverter using unipolar pulse width modulation. Unipolar means in single direction. That is polarity will be 1. This can be better understood by using this. So first we will generate the levels at the DC and then we will provide it to the H-bridge inverter in order to get the AC output, multi-level AC output. Okay, here this is the switching table for that multi-level inverter. This is the multi-level inverter topology. It consists of 10 switches, 6 switches for generating the levels and 4 switches for providing the inverter operation. And these are the conduction device. There is switching pattern for the multi-level output. Here 4 levels in the positive level and 4 levels in the negative level, and with 0 level we will get 9 level output. VDC1, VDC2 minus VDC1, VDC2, VDC1 plus VDC2. So these are the 4 levels we will get at positive cycle, and in negative cycle 4 more levels, and with 0 level we will get 9 level output. This is the simulation circuit. Here if you see means 3 plus 2 plus 1, totally 6 switches for level generation and 4 switches for polarity, that is for inverter operation. And the pulses are provided according to the switching table. Here these are the modulation waveform and carrier waveform used to generate the pulses. And from that pulses are generated and it is provided here. Okay, for first 4 switches, first 5 pulses is for the level generation and next 2 pulses are for the H-bridge inverter operation. And these are the output voltage and current waveforms. Here, level 1, 2, 3, 4, 5, 6, 7, 8, 9 level we are getting. Due to the inductive load, that is RL load, here we will get the output current as nearly sine wave. And here the input voltages is in the ratio of 60. VDC1 is 60. VDC2 is 180. That means 1:3 ratio. So the total output will be VDC1. That is maximum voltage will be VDC1 plus VDC2. That means 240 volt we will get. And we have to measure the THD value. FFT analyzer. Fundamental frequency 50. Okay, here the THT is in the range of 17.15. We have to run the simulation again. Okay, here the current THT is around 1.22 percentage. Okay, here there are 10 switches totally. We have to reduce the number of switches. So here instead of this back-to-back switches, we will introduce one more switch. We will replace the back-to-back switches with a single switch and a diode bridge setup. Here if you see means this is the setup for back-to-back switches. Although the number of diodes is increased, we are reducing one switch, so that in hardware, if you see means while implementing it, that driver circuit parameters, that whole setup will be reduced here. And during that is when it is in the positive cycle, it flows from this point to diode. Here the switch will be on and to this diode, and it will flow through the next end. And in the negative direction, that is negative cycle, it will flow from this point, this diode, this switch will be on, this diode to this point. So it can be operated in both directions. Now again, we will run this simulation to get, we can get the same output or not. The voltage, everything will be same here. V160, V2 will be 180, that is 1:3 ratio. And the output voltage, okay, if you see means the output voltage is same. Okay, voltage, maximum voltage is also same. The levels are also same. 1, 2, 3, 4, 5, 6, 7, 8, 9 levels. So by even after reducing one switch, we can get the same output for same input voltages. And still we can reduce that number of switch. Here, we already reduced that back-to-back switches with the help of this bridge setup and one single switch. And here, instead of a switch, we are using a diode. And the diode resistance will be higher than that of the IGBT. So when this IGBT is on, the current flow will be in this direction only. And when this IGBT is off, at the time, the current will flow through this diode for positive cycle. Again, we will run the simulation. In this, the total number of switches are 1, 2, 3, 4, 5 for level generation, 3 for polarity. So totally 8 switches. Here if you see means 1, 2, 3, 4, 5, 6, 7, 8. Still the number of levels are same only. Compared to the previous topology, we have reduced 2 switches. Still it is same only. And we can modify this setup, that is topology, by changing the voltage ratio. Here instead of 1:3, here if you see means 60, 180. That is, it is reversed, 3:1. The voltage ratio is 3:1. By changing that, we can get the number of switches as 3 plus 4, 7 switches. So initially it was 10, then it was reduced to 9, and then it was reduced to 8. Now we are getting 7 switches. Again, we will run the simulation to check whether the same outputs we are getting. Okay, if you see here, still we are getting the same results. 1, 2, 3, 4, 5, 6, 7, 8, 9 levels we are getting. So even if after we reduce it here, the number of switches from 10 to 7, the levels are same only. Simply we have changed that voltage ratio from 1:3 to 3:1. Okay. And again, we can reduce that number of switch by changing this switch, that is replacing this switch with one diode. Okay, now if you see means 3 plus 3, totally 6 switches are there. For 6 switches, we should get 9 levels. Okay, we will check the results now. Here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Still we are getting the same number of levels even after we reduced the number of switches. From 10 switches to 6 switches we have reduced now. And we have changed the ratio also. Initially it was 1:3 ratio. Now it is 3:1 ratio. So these are the results we are getting for various topologies of multi-level inverter.